All right, today we are on a mission. Think of it like a molecular manhunt. We are going to track a single, tiny molecule, caffeine, as it pulls off this incredible, daring escape from its prison inside a tea leaf.
So here's the big question, right? A tea leaf, it's just this complex jumble of millions, literally millions of different molecules. How in the world do you reach in and just pluck out the one specific molecule you want, leaving everything else behind? That's the puzzle, and chemists have this beautifully elegant technique to solve it.
And that technique is called extraction. The best way to think about it is like this. We give the molecules a choice. We offer them two different liquid homes, and based on who they are chemically, they'll pick the one where they feel most comfortable. So our job really is to make the home we've built for caffeine so incredibly inviting that it just can't wait to escape on its own.
Okay, so like any great escape, there are rules. And in chemistry, the biggest, most important rule of all is super simple. Like dissolves like. That's it. This one little principle basically governs which molecules are going to be friends and which ones are going to stay far, far away from each other. You see, we're working with two totally different molecular worlds. On one hand, you've got the polar world of water. This place is perfect for anything with a charge, like salt. Water uses these really strong hydrogen bonds to just pull them right in. But then you have the organic world. This is the world of a solvent like dichloromethane, or DCM for short. And this is the preferred home for neutral, nonpolar molecules, which is exactly what our target, caffeine, is.
And I mean, just look at the numbers here. It's not even close. In water, caffeine solubility is, 22 milligrams per milliliter. Okay, but in DCM, it's 140. That is a huge difference. It's like a 7-to-1 preference. So you give caffeine the choice, and it is overwhelmingly going to pack its bags and move right into the DCM. This huge preference is the engine that's going to drive our entire escape plan.
You know, chemists actually have a way to put a score on this preference. It's called the partition coefficient, or KD. Don't let the formula scare you. It's just a simple ratio. How much of our molecule is in the organic layer compared to the water layer? Bottom line, a higher KD number means it really wants to be on the organic side, which means our extraction is going to be way, way more efficient. All right, so we get the rules of the game. Now let's get into the nitty-gritty. Let's walk through the actual step-by-step escape plan that we're going to use to guide our caffeine molecule all the way from the tea leaf to a pure, isolated crystal. And believe it or not, the very first step is something you might have already done today. It's making a cup of tea. Seriously, when you pour hot water over tea leaves, you're actually performing what's called a solid liquid extraction. The heat and the water team up to break that caffeine free from the solid leaf and pull it right out into the liquid. You're a chemist and you didn't even know it. Okay, so here's the full lab procedure, the whole shebang. After we've brewed the tea, we're going to add a chemical to trap some impurities. Then we add our organic solvent, the DCM. That's our getaway car. We give it a good, gentle shake to mix everything up, then we let the layers separate. We drain our prize, we dry it, and finally, we evaporate the solvent. It's a clean, logical path to freedom for our caffeine. But hold on a second, let's back up. Step 1 there, add NaOH? Sodium hydroxide? That sounds pretty intense. Why are we putting that in our tea? What's its job in this great escape? Well, it's actually a really clever bit of chemistry. The NaOH acts like the perfect diversion. See, tea has other stuff in it, like tannins, and those are acidic. The NaOH reacts with them and slaps a negative charge on them. And what do charged things love? They love the polar water layer. So just like that, the tannins are trapped in the water, leaving our neutral caffeine molecule totally free to sneak away into the DCM. It's brilliant. So we take our tea and our DCM, and we put it in this special piece of glass called a separatory funnel. And the instructions are always clear. Shake it gently. But what happens if you get a little carried away? You know, you're excited, you're in the zone. What happens if you shake that funnel too hard? You create a major obstacle, an emulsion. It's this stubborn, murky mess where the two liquids just refuse to separate, and that grinds our whole extraction to a halt. Shaking too hard just creates these tiny little droplets that get all suspended in each other. But don't worry, there's a fix. This is a classic chemist trick. You add a really concentrated salt solution called brine. This is known as salting out, and it makes the water layer so polar that it just forces the organic stuff out, breaking up that messy emulsion. Okay, now here's the key strategy, and this might seem a little counterintuitive at first.
To pull off the most effective escape, it is way better to wash the tea with 3 small portions of DCM instead of 1 big one. Just think about rinsing a sticky syrup cup. If you do 1 quick rinse, you always leave some behind, right? But if you do 3 smaller, focused rinses, you can get it perfectly clean. It's the exact same principle here. Multiple extractions are how we recover the absolute maximum amount of caffeine.
Okay, we did it. We've successfully moved the caffeine into our organic solvent. But the mission is not over. Not yet. Now we have to do the final polish to make absolutely sure that what we have is pure caffeine and nothing else.
So first up, we use a drying agent. You can think of it like a tiny chemical sponge that soaks up any last little bits of water. Then we gently evaporate the DCM solvents, and that leaves behind our crude caffeine. But for the ultimate purification, the gold standard, we use a technique called recrystallization. We dissolve our caffeine in a hot solvent and then let it cool down really slowly. As it cools, the caffeine molecules have time to find each other and arrange themselves into this perfect, beautiful crystal structure, literally pushing any remaining impurities out of the way. So how do we know for sure? How do we know our escape artist is truly pure? We check its melting point. See, a really pure compound has a very sharp, very precise melting point. If your stuff starts to melt over a wide range of temperatures, or at a temperature that's too low, well, that's a dead giveaway that you've still got some impurities hiding out in there.
We've been following caffeine's journey in pretty incredible detail, right? But now let's zoom out for a second. Why does this one technique, extraction, matter so much? What's the bigger picture here? It matters because extraction is, well, it's everywhere. It's used to isolate medicines from plants. It's used to purify compounds after a chemical reaction. It's used in the food industry to create flavors. This isn't just some niche lab trick. It's one of the most fundamental tools a chemist has. It really is like a chemist's Swiss Army knife. And that brings us right back to where we started. So the next time you brew a cup of coffee or you steep some tea, just take a second and remember the great molecular escape that's happening right there in your mug. You're not just making a drink, you're running a tiny and hopefully delicious extraction experiment, all thanks to the simple but really powerful rules of chemistry.